In the last lecture of this chapter, let us look at the nature of dependencies in an out-of-order pipeline and the problems that these dependencies can cause. So we have looked at the program order dependence. So this is rather simple. So this is essentially the order of instructions that appear in the original program. So this is one instruction and this is the instruction after it. So this is a program order dependence. And we have already distinguished between the terms a static instruction and a dynamic instruction. So a static instruction, a classic example would be, let's assume we have a for loop. So the for loop will have a set of assembly instructions with a jump, of course, a backward jump. So how do we detect a loop in hardware? Well, it is simple. Any jump with a negative offset is essentially, well, not most of the time, it points to a loop because we go back, again we start executing, again we go back, right? It's a loop. So if you see here, there are 1, 2, 3, 4, 5, there are 5 static instructions. But if the loop has 100 iterations, it is 500 dynamic instructions. So here one instruction appears after the other in program order, and we always talk about the dynamic sequence in our discussion. So the program order is simple. We have seen that, no major issues. Now let us discuss read after write dependencies. So these are the dependencies that were causing a lot of issues in in-order pipelines. So in in-order pipelines, basically this was a classic producer consumer dependency. Where the first one is the producer instruction and the second instruction is the consumer instruction. So in this producer consumer dependence, we found that the consumer always has to execute after the producer. So this order you need to maintain both in an in-order pipeline as well as in an out-of-order pipeline. So hence this is called a true dependence because there is no escaping. The producer executes first and the consumer executes next. Alright, so now let's move on to two other kinds of dependencies which were not causing an issue in in-order pipelines, but they will cause an issue in out-of-order pipelines. So consider this piece of code where the write to the same register R1. So essentially the destination is the same. In this case, since they write to the same location, and of course this is the program order, it is not possible to reorder these two instructions. We cannot reorder them. So even if we were to execute them out of order, the way the instructions stand, we cannot reorder, because let us say this is writing 3 to R1 and the next instruction is writing 5, right? And the first is instruction 1, then 2. If we execute instruction 2 first and then instruction 1, then the final value of R1 will be equal to 3, which of course is wrong. The final value of R1 should be equal to 5, which means that in all out of order executions, we cannot break this write after write order, which is also, or a write after write dependence, which is also called an output dependence. This cannot be violated, right? So this of course is not a true dependence. We will see why in the course of the next few slides. It is actually what is called a false dependence. And let us look at this closely. If we look at this closely, what we will actually get to see is that the reason we have such dependencies in assembly code is basically because we have a finite number of registers. So if I had an infinite number of registers somehow, then instead of sending the output to R1, I could have sent it to R20, right? So every time if I use R1, whenever I have R1, if I actually assign it to a new register, then I will never have an output dependence. But since I have a finite number of registers, I need to reuse registers. This is where the output dependence comes in, right? So this is essentially an artifact of the finite number of registers. All right, let us look at the next kind of dependence, which is a write after read dependence. It's also called an anti-dependence. So let us look at the first instruction, instruction 1. So in instruction 1, we are reading from register R2, and in instruction 2, we are writing to register R2. So the first is a read and the second is a write. So we have a write after read. So for similar reasons, we cannot reorder these two instructions. If we reorder them, we'll end up with the wrong value. It is possible that the value that instruction 2 writes, instruction 1 will read it, which of course is not correct, it is wrong. And this again arises, this is known as an anti-dependence. This again arises because we have a finite number of registers, right? This is also an artifact of, this problem that we have a finite number of registers, right? Correct. So in this case, also, if let us say that we have some method, some mechanism where every time we use we never repeat registers, in the sense we write to a register once and we keep on reading from it. So essentially, if we have this model, write once, read many times, so we will actually not have both WAW, output dependencies, and anti-dependencies. And the reason for that is that every time we write to a register, it will actually be a new register. So this requires an infinite number of registers, which of course is not feasible, but we will see that we can do something to get rid of both output dependencies as well as anti-dependencies. All right. So this is something that we need to do, and we will see. All right. So now let us come to the next category of dependencies that we have seen. They are known as control dependencies. So here, well, it's rather simple. We jump to a label, and when we jump to a label, we execute instructions after it. So even in out of order pipelines, if we do not predict the branch correctly, so in out of order pipelines, of course, we have to predict branches. If we do not predict branches correctly, we stand to fetch instructions from the wrong path. And wrong path instructions will pollute the instruction window, and as we have seen, they have to be discarded, they cannot be executed. So they cause a lot of issues. So that is why we needed a very accurate branch predictor. So out of order, in out of order issues, control hazards are actually even more important, much more important than they were in order processors. So some basic results, well, in order processors respect all program order dependencies, in the sense they execute instructions in program order, whereas so this means that they execute both, they respect all data and control dependencies, Whereas out of order processors will only respect data and control dependencies. So let's gradually understand what this means. All right. And so it is important for us to kind of gradually see and understand what this means. Primarily, out of order processors respect data dependencies, which are producer consumer relationships. They appear to respect all dependencies, including control. So the way that they appear is that if you have an if statement, we predict the direction of the branch and then we fetch instructions after it. We can very well execute these instructions before we execute the if statement, if they are independent, that is, right, independent from a data perspective. And then we execute the branch corresponding to the if statement at a later point of time. And if that is fine, well, we don't do anything because we have anyway predicted it correctly. So in a certain sense, this data dependence is broken. But of course, control dependencies, which basically means that we need to always follow the correct path, that of course all processors need to do, both in order as well as out of order. So now the question is, can output and anti-dependencies be removed? So what we have been arguing up till now is that they are an artifact of a finite number of registers. So let us take a look at these two examples. So in this example, in the first one, we are writing to R1, as you can see. So there is an output dependence. In the second example, we have a write after read kind of situation. So we basically read from R2 and then write to R2. So if we look at it, if we think about it, both of them can be conceptually, both the situations can be conceptually represented on this timeline, where essentially set the value of a register, let's say it is R1. We then have several read instructions that read its value. Again, so this is like the first avatar of the register, which is R1. And then we have the second avatar, which sets R1 again, which as you can see, it sets it again. And again, a couple of instructions read. So as far as we are concerned, the first avatar over here starts with a write, has a bunch of reads. Again starts with a write, has a bunch of reads. So of course it need not have a bunch of reads, it can have no read as well, but at least it needs to start with a write. So the typical pattern would be you write, then you read, then you write, then you read. So the value that has been set by this instruction, the value of R1, that has been set by this instruction, that will be read over the subsequent instructions. And so essentially the lifetime of this avatar over here can be captured, is kind of in a sense represented by the value that has been put into R1. And similarly, a subsequent avatar starts. So if, let's say, automatically we change R1 to, let's say, R100 and then replace every single use of R1 with, I'm sorry, this should be use, and then replace every single use of R1 with use of R100, it will make no difference at all, and the programmer will not be able to see the output of the program will still be the same, and essentially everything will work in exactly the same manner as long as we are consistent, which means that every read that uses this value of R1, that instead of using R1 uses R100. So this process of actually taking a register and renaming it to another register is known by the word renaming, right? And as you can see, what renaming does is that for each avatar of a register, it assigns it a different register, right? So we will see the advantages of renaming very soon. So let us see what it does. So let us take a look at this piece of code, where this is a piece of code that the compiler has generated. So it does have architectural registers, and which are our normal registers. So normal registers are known as architectural registers in this particular context. So as you can see that because we have a finite number of registers, registers are repeated. So we write to R1, then we write to R1, then we write to R1 again. So now let us assume that we have an infinite number of internal registers which are called physical registers. So of course in practice they are not infinite, but for the time being let us assume it will make our life very easy. So let us say we have a finite number of architectural registers, and we have an infinite number of physical registers. So what we do is that, so this is just a convention for this example, that register Rx is mapped to physical register Px with the number of the avatar. Alright, 1, 2, 3, 4, 5, 6 and so on. So consider the first instruction, R1. So R1 we map it to P1, and since it is the first avatar, we say it is P11, and so move R1 1 internally. So it is who does this process? Well, the hardware has a renaming engine, and the process, this conversion from an architectural register to a physical register happens internally. All right. So the hardware does it internally, unbeknownst to the programmer or the compiler. It is kind of invisible. It happens internally, and internally they are mapped to a new set of registers. How that happens? Well, we will see in the next few chapters. Currently, I am just introducing the problem conceptually. So, I am making some assumptions which will later on we will see they will not hold, but that doesn't matter. Now, let us assume that R2 and R3 were initially mapped to P2 and P3. So, you will get the values from there. Since we are creating a new avatar of R1, we create a new physical register, map it to a new physical register, which will be P1, second avatar P12. The third instruction is rather important. So here we are using the value of R1. There is a read after write dependence over here. So R1 we will use the latest value that has been written, which is essentially the current avatar, and this has been P12. So we use P12 over here. Since we are writing to R4, we create a new avatar of R4, which is P41, and we proceed. Now coming to the next instruction, we are writing to R2. This is the first avatar of R2. So we move 5 to P21, right? The pattern should be clear by now. Furthermore, after a set, we have a use. So the use will of course use the current avatar, and R2, the use, it will use the physical register P21 because P21 is using the current value. R8 is mapped to P8, R6 is mapped to P61. All right. So that is the first avatar, because we are not written to R6 before. And finally, we write to R1 again. So the moment we write to R1 again, we create a fresh avatar of R1, which is P13. And so basically P13 essentially means that we are creating the third avatar of R1, right? And we are writing 8 to it. So kindly note that this particular convention is only for this example. So we will generalize it later. But currently our focus is on understanding this concept. Finally, we'll use R1. Which version we'll use? We'll use P13. And then we will use R2. Which version we'll use? The latest version, which is the one written over here, P21. And we'll create a new avatar of P91. So this is the code with physical registers. So let us look at this closely. So what you see is that whenever we write to an architectural register, we actually create a new avatar of it, right? So we create a new avatar of it, and so then we essentially set. So we write once, we read many times. Again, we create a new avatar of it, right? Which is a write. These are all reads. Again, we create a new avatar and we read. So let us look at each of our dependencies. The read after write dependency, well, that is holding because we are always reading the latest version. Write after write dependencies, well, there are none because we are assuming that we have an infinite number of physical registers. So we will never actually write to the same register twice. Given that we are not doing that, there will be no write after write dependencies, right? Hence, we do not have to bother about them. What about write after read dependencies? Well, again, we will not have to bother because the read is using the previous avatar. So just take a look at this. For R1, the read is using P12, and after that we are writing to R1 again, right? Which is this version P13. So there is a write after read dependence over here, but this is not causing an issue because these are actually separate avatars. They are in separate registers. So even if we were to reorder these two instructions, it will make no difference at all because they are actually writing to different registers. Sorry, they are reading and writing, they are accessing different registers, right? So the write after read is an issue only when they are accessing the same register. But now since we give a different physical register to each avatar, write after read issues will simply not happen because after a read, the write will write after a read to an architectural register. As you can see, the next write will actually write to a different physical register. So we will actually not have any write after read dependencies. So given the fact that we will not have these dependencies and they have been removed with this renaming mechanism that I am proposing, they are false dependencies in the sense they can be automatically removed, right? It's only the read after write which is a true dependency. So now this is another, so let me erase the ink on this slide and I can take you through this, through the animation. So as you can see, there is a write after write dependence over here, but there is no such dependence on the right side. The read after write dependence is clearly visible, right? They are mapped to registers of the same avatar. Again, another read after write is clearly visible, and another, as you can see, read after write is clearly visible, but nothing else is visible, right? So there are no other dependencies. So we did draw your attention to a write after write problem, but as you can see, it's not over here. So what does renaming actually do? Well, it takes a program with real registers, architectural registers, that has three kinds of dependencies: read after write dependencies, write after read dependencies, and write after write dependencies. So they have three kinds of dependencies. And so then the process of renaming, which is automatically done inside the processor and nobody can see what's happening, neither the programmer nor the compiler. Right? So this converts the program internally, of course, not visible outside. Right? Internally, of course, so it's not visible outside. It converts it to a program with physical registers. So a program with physical registers has only raw dependencies, read after write dependencies. And of course, as you can see, fewer is the number of dependencies, fewer are the dependencies, higher is the instruction level parallelism, the ILP, right? So since we reduce the number of dependencies, we have exposed more instruction level parallelism, which is something that the program can use to find more independent and parallel instructions that can be issued at the same time. So where are we now? Well, we have the design of a proto out of order processor where we read instructions from the iCache. So we are generally referring to this as the instruction memory in this slide set. Then of course we need a branch predictor. We all have seen why, such that we can quickly fill the instruction window. Then we'll have our regular stages of fetch and decode. After decoding an instruction, we have to rename the instruction such that that is essentially to remove these two kind of dependencies, so they need to be removed. Then we need to read the value of registers. So basically this process can be done after it. So it is better, I delete it. It's a small error over here in this slide. So this is actually done slightly later. The register read is actually done slightly later at this stage. So we will discuss that later. All right. So not now. And so then we create a large pool of instructions. So every cycle we find a set of ready instructions, so the operands are ready. And then these independent ready instructions are sent to the execution units, not one but several in parallel. The results are computed and then we write back the results to the register file. So this is kind of the design of a simple out of order processor as much as we have seen till now. So now let us look at the write back process. So the write back process has some issues. These issues have to be addressed, these issues have to be fixed. So let us look at the processor from outside. Let us look at it as a black box. So in the black box, instructions come in and then the processor updates the state, which is the state of the register. So of course outside the processor we don't get to see the physical registers. These are the regular architectural registers which the compiler and the rest of the world sees are regular registers basically. So this architectural register file gets updated and the memory gets updated, the data memory gets updated and the register file gets updated. So to an outsider, should it matter if the processor is in order or out of order? Well, the answer is absolutely no. The outsider should simply not care whether we are using an in order pipeline or an out of order pipeline, right? So it should not concern the outsider at all. It should not concern the outsider to the least bit what kind of processor is actually being used. All right. So given the fact that externally we want the behavior to be the same, how do we ensure that? So let us elaborate on this topic. So assume that there is an exception or interrupt. So why? So we are executing. So assume here we divide by 0. So whenever we have a division instruction, we can have a divide by 0 problem. So then there are several options. One is that the program can crash. So this is true for a simple program, but consider that you are running something on Excel and you divide by 0. Does Excel crash? It doesn't. What it does is it tells you that look, you have divided by 0, that's an illegal operation, and then Excel continues its operation, continues its working. So in most mature software, we actually have an exception handler. The exception handler is another small function which is called, it shows you a message on the screen that look, you have divided by 0, that is an illegal operation, and then we either continue executing from there or we jump to some other function and start executing that. So this is the typical flow of a program whenever an exceptional condition of this nature is encountered. So almost all high level languages such as C or Java have features to write your own exception handlers if the programmer somehow messes up, but you still don't want the program to crash. The important question over here is that should the sub instruction, so let's say our exception handler is called over here, right? And let's assume it does something and then again it comes back. So at this point when the exception handler is running, should the subtract instruction have completed, what about the subtract instruction, right? In an out of order processor, it is very well possible that these instructions could have been reordered. So it is possible that the subtract would have completed its execution, written the value to R4, and then since the execution is out of order, the divide instruction would have executed, had a fault, and gone to the exception handler. So before telling you why this is incorrect behavior, let us first tell you that an in-order processor will never do this. Why not? Well, the reason it will not do it is because it executes instructions in program order, right? One after the other. First this, then this, then this, and then this. So if there is a problem in the division instruction, it will immediately stop the execution, not process the sub instruction, subtract instruction at all, move to the exception handler, do whatever that the exception handler says, right? And the instructions in the exception handler, execute them, come back, and then execute the subtract instruction. So from the point of view of an outsider, the outsider will essentially see execution in full program order in the in-order processor. However, in an out-of-order processor, if we jump to the exception handler, we are setting ourselves for extremely difficult, non-intuitive behavior where the outsider might see that the subtract instruction has completed or God knows what. You can see a full mix. It is furthermore possible because of out-of-order execution, right? Maybe some other instructions from here, they have not completed, all right, which are way before it in program order, they have not completed, and maybe instructions after Dave have completed. So in that case, it is not possible to actually stop the program at one point and restart it. And of course, there are other things. So normally what happens in a modern operating system, we run multiple programs in parallel. So of course, we never run multiple programs in parallel. What actually happens is we run one program for some time. Then we have a timer chip, right? So the timer chip is outside the processor. It sends an interrupt. So the interrupt basically says that look, your time is up. Then the operating system loads another program on the processor. After some time, the timer chip again tells, look, your time is up. So that is why there is a need to effectively stop a program at one point and restart the execution of the program at the same point. So not only is this very helpful from the point of view of an exception handler, it is also very helpful from the point of view of an operating system, which essentially sends an interrupt to the program, makes it stop at a certain point, and then resumes the program at the same point. If let's say things were executing out of order, something before this has finished, something before this point has not finished, something after it has finished, the stop and resume will become very hard, right? So what we want is we need the power to arbitrarily stop the program at points and then resume the execution. So what is important for us is this stop and resume behavior, and this is not possible, appears to be very hard in an out of order execution. So what we define is the notion of a precise exception. But the flow of action should be as follows. We have our regular instructions before the div, which means all of these. Then we see the divide by 0. Then we load the exception handler. And then we execute the subtract instruction. Alternatively, it is possible that maybe there was no divide by 0, but the operating system decided to shell the program and run another program on the core. So know that operating system is also a program, right? So it's nothing special, but there is an external timer chip which essentially sends the interrupts. The operating system pre-programs the timer chip, and the timer chip, which is an external entity, sends an interrupt. And so then the entire state of the program is stored over here, and the exception handler in this case is the OS. It will load another program. So what we want is we need the stop and resume semantics. So in a stop and resume semantics is very easy in an in-order processor because we are following program order. We execute, stop at one point, no problem, and we just store the register state and then go and execute some other program. With out of order, it's hard. So what we want is that we want all external agents, which is anybody sitting outside the processor, to actually look at the processor and not be able to say whether it is out of order or in order, which means that internally an out of order processor can do whatever it wants, but externally it should appear to be as if it is an in order processor. What do I actually mean? What I actually mean is that externally, which means if this is the processor and I have a pair of eyes, and if I have a pair of eyes looking at it externally, they should see this order, the regular instructions, divide by 0, exception handler, and the subtract. They should not see this order, which is regular instructions, divide by 0, the subtract, and then the exception handler. This is indeed out of order, but out of order should be visible inside, not outside, which means that to an external observer, the execution should always be correct, should always be as per program order. Even if there are interrupts and exceptions, externally it should be in program order. So this is making our life very difficult. So this is a rather complicated thing that we are just discussing. We are saying that, look, if you want a seamless stop and resume of a program to an external agent can be anybody. An external agent can be the programmer, can be the compiler, can be the operating system, or can simply be an oscilloscope that has probes outside the processor. Doesn't matter. An out of order processor, right, should appear to be. So this will kind of keep our life very simple, right? Internally, it can do whatever it wants. So what are we saying? We are saying that, look, for outsiders, you appear to be an in-order processor. Internally, you do whatever you are doing. You want to execute out of order, no problem, do it. How do we ensure both at the same time? Well, chapter 4. So in chapter 4, we will discuss how to do it, not now. But at least for us, this is a goal. So this chapter is all about goal setting. This chapter is all about telling us what is it that we expect from the out of order processor. And a crucial aspect of this goal setting is this particular requirement. So this automatically takes us to the notion of precise exceptions, which means that the following. So let's first define the terminology. Let's say the dynamic instructions in a program are numbered instruction 1, 2, 3, 4 up till n. Assume that the processor starts the exception interrupt handler after it has just finished writing the results for the kth instruction. To an outsider, it should appear. And as I said, outsider is very generic, can be the programmer, compiler, operating system, or even an oscilloscope that has probes plugged in to the interface of a processor. It should appear as if all of these instructions have executed completely, written their state to the memory or register file, and none of the instructions after this have even started. So these are fully done and these haven't even started. Right, so I should have a not started in bold, right, not started, and these are done, and this is of course where we have the exception. So we have an option at this point of stopping the program, storing its state, which is easy. We just need to store the value of the architectural registers at this point, process the exception, and resume. Right, stop, resume. For a seamless stop and resume, what you will agree with me that the first k instructions have to be fully done, and all the instructions after it should not even have started. So this notion is known as a precise exception, and almost all out of order processors as of today provide the notion of precise exceptions, which essentially means same things which are all equivalent, that outsiders see right, outsiders will see an in order execution. So basically, so the processor in this case consists of the cores, the core and pipelines are the same, and of course the memory. So let me just, all the memory that you are using doesn't matter, let me just draw a full circle around them, that's a black box. So any outsider outside this black box will see in order execution, right, which will allow us to essentially stop the program at some point. So we are sure everything before this is totally done in program order, execute the exception handler, and again restart at the same point. So we are sure that nothing after the kth instruction has even started. So this ability is very important. Not only is it required for intuitiveness and correctness, it is also required for processing exceptions, as we will see. It is also required for recovering from branch mispredictions, because even that is an exception. We will also see that it is a very vital requirement for operating systems, because what normally happens, if I can use some of the additional space over here, what normally happens, just do a control alt delete, and you will see. So in fact, let me do that right now. So what you can actually see over here in my task manager, that look, I have a lot of tasks, and you can see your PowerPoint task over here. So if I have a single core, what I'm actually doing is that I am running multiple programs, right, program 1, program 2, program 3, etc. on the single core. So on a single core, what will actually happen is that program 1 will execute till some time. As we have said, we will have a timer chip. It's very important to have the timer chip. It's not a part of the operating system, it's a separate piece of hardware. It will send an interrupt. It is typically programmed to send an interrupt once every 1 millisecond. Once that happens, what the processor does is that it saves what is called the context of the program. The context is simple, it's the program counter and the set of architectural registers. right? Because the physical registers are not visible to software. So it's essentially the program counter and the set of architectural registers that is saved. And then, well, it starts executing some other program, maybe program 2. Again, after 1 millisecond, another timer interrupt comes. The operating system then might decide to start executing program 1 back again from exactly the same point, and you will not perceive a difference. It's like magic. So what's happening over here? What is happening over here is that unbeknownst to program 1, we stopped it at one point in the middle. We executed another program. Again, we brought program 1 back. We were able to, because program 1 supports precise exceptions, we were able to nicely restore its state and execute it from that point. So operating systems, what they do is that they take a small chunk of program 1, execute it, then execute program 2, then execute program 3 maybe, then 1, then 2. Maybe they execute program 2 for several time slices, where one time slice is defined as 1 millisecond. And if we have tens of programs, as you just saw, then maybe, you can take all of these programs and just, execute them in any order. The reason we don't perceive this is because this is happening hundreds of times a second. So it is happening so quickly that we actually don't perceive the fact that the operating system is actually executing lots and lots of programs quickly, one after the other, on the same core. So of course, if we have different cores, where a core is basically just an encapsulation of a pipeline, then of course these programs can be run on separate cores. But even if we have a single core like in the good old days, the operating system can happily switch between these programs, what is known as multitasking, and just keep switching between them hundreds of times a second. We will never be able to perceive what's happening. And the reason that we are able to switch is because there is a way to stop a program at a point and resume it from exactly the same point. This stop and resume behavior is enabled because we have precise exceptions. And what are precise exceptions? Well, they just say that, look, for a pair of eyes outside the processor memory black box, they essentially perceive in order execution, which means that all software entities, be it the programmer, the compiler, the operating system, all of them perceive in order execution. Even the inside the processor, we are actually doing out of order. So our important challenge, most important challenge would be, or our motto, out of order inside, in order outside. So out of order inside will give us what? It is going to give us performance. In order outside will give us simplicity, intuitiveness, and correctness. Right? Correctness from the point of view of seamlessly stopping and resuming programs. Right? So where have we stopped? We have stopped at a nice point where we say out of order inside, in order outside. And precise exceptions are a natural corollary of the in order outside philosophy. Now we come to the last slide of this lecture set. So this talks about the 5 most important points that we have learnt in this chapter. So the first is that in order pipelines, which we have studied with so much of pleasure in our undergraduate texts, have a limited IPC because of branches and data hazards. If I were to have a complex multi-issue in order pipeline, that is not really going to solve the problem. The reason being that there will be a very complex structure of dependencies and interlocks, hence the problem will not get solved. What we instead need to do is we need to change our thinking and we need to go for out of order processors. Alright. So in out of order processors, we need a large instruction window to find a sufficient number of independent instructions. To sustain the large instruction window, we would need a very accurate branch predictor, right? So we have looked at some accuracy numbers, but something like 97 to 99% is the minimum that we need, right? More, not less. Moreover, to expose additional ILP, instruction level parallelism, we can remove, I stand corrected here, write after write and write after read hazards by renaming. Alright. So for additional ILP, we can remove the false dependencies or the write after write and write after read hazards by renaming, which essentially assign a separate physical register to each avatar. Finally, for the sake of correctness, we need to ensure precise exceptions such that we can transparently, seamlessly, and easily stop a program at an arbitrary point and resume the program at the same point after a long time. Alright, so I will meet you in the next chapter, which discusses the fetch logic and branch prediction in great detail.